Hello, everyone. It's welcome to Chemistry 4502, Lecture 11 on the hydrogen atom. It's me, James Johns, probably better known as your chemistry professor. In today's lecture, we're going to be talking all about the hydrogen atom and incorporating some of the stuff that we learned on Friday about angular momentum into our solutions for the hydrogen atom, and really getting a better understanding of what the energies and the eigenfunctions for the hydrogen atom actually are. Okay? So, with that, we're going to dig right into it. So, the hydrogen atom is probably the most important atom in all of chemistry. It's the building block of how we think about chemistry. Hydrogen orbitals are the basis for molecular orbital theory. It's how we think about bonding in organic and inorganic chemistry. The shape and energy of hydrogen bonds, of hydrogen orbitals, will subsequently be applied to multi-electron atoms and molecules in this class. It was also the very first quantum mechanical triumph. Erwin Schrödinger wrote his paper in 1926 in German that I can't possibly pronounce, Quantisierung als Eigenwertproblem, in the Annalen Physics in 1926, in which he solved the hydrogen atom. He didn't start with a simple problem like particle in a box or particle in a ring. No, he went straight for the hydrogen atom. That was the first thing he solved. The other reason, the final one why this one is so important, is that hydrogen-like atoms, or atoms that have only a single electron in them, are the only atoms that we can solve for their wave functions and energies exactly. Right? So for the hydrogen atom, we can really just nail this down. If we have something like helium 2+, which would be a helium with one electron missing, that would be a one electron atom. We can nail that down. Lithium 2+, beryllium 3+, etc. Any one electron atom we can do using the same basic approach as for the hydrogen atom. Okay, so this is our first case where we have a potential energy that isn't zero, and so we have a new system, the hydrogen atom, and we need to know what its potential energy is so that we can write down its Hamiltonian. Once we have its Hamiltonian, we're going to look for eigenfunctions of that Hamiltonian to find the states that have well-defined energies. So, hydrogen atom. Here we have a proton in blue, which is the nucleus, and an electron that's orbiting it. Okay? And we have some distance between them, r. The potential energy associated with these two charges is simply the Coulomb attraction. So we have minus z, which is the atomic number, the number of protons we have down here in our nucleus, which for hydrogen, of course, would be 1. E squared, where E is the fundamental charge constant of the universe. It's the charge of the electron. So we have times 1 over 4 pi epsilon naught. That's the dielectric permittivity of free space. Times 1 over r. The most important part is that 1 over r, right down here. Right? So this potential energy changes when the electron is really close. It's strongly attracted to the nucleus. When the electron is far away, it's much more weakly attracted to the nucleus. Okay? So once we know our potential energy, we can then write down our Hamiltonian for this. Right? So our Hamiltonian for the hydrogen atom is the sum of the kinetic plus potential energy. The kinetic energy minus h bar squared over 2 me, or mass of the electron. We're going to assume that the nucleus is fixed here. The nucleus is, in reality, this me should probably be mu, the reduced mass of the electron and the proton. But the proton's over 1,000 times more massive than the electron. And so we make a really good approximation just by leaving that m sub e. So minus h bar squared over 2 me times the Laplacian, minus our potential energy. Okay, so the potential energy only depends on the distance. And so it makes a very natural thing to do is to not work in Cartesian coordinates, but instead to change this into spherical coordinates, just like we did for angular momentum. But before we do that, let's talk about what we're trying to do. So, this is the first time we're really looking at a real physical experimental system where we have real physical data that we can compare our results to. So before we had quantum mechanics, we had these series called the Paschal series, the Balmer series, the Lyman series, and these were wavelengths that the hydrogen atom would emit and absorb light. And phenomenologically, it was determined that there was this relationship between them where the energy of the photons that were absorbed were proportional to some number, which we call the Rydberg constant, times 1 over an integer squared minus 1 over an integer squared. Okay? And the Bohr condition, Niels Bohr came along and said, well, what must be happening is that we're absorbing light. We're going from one quantum state to another quantum state. And so this is really some number associated with the final state and some number associated with the initial state. Now, if our treatment of the hydrogen atom is going to make any sense, we need to be able to reproduce energy levels that can give us an energy spectrum like this. And that's what we're going to see if we can do during the course of this and the next lecture. So our goal for the hydrogen atom is we want to find the set of wave functions, psi of r, theta, and phi, that give us energy levels which can then reproduce the hydrogen atom absorption and emission spectrum. Once we can reproduce that data, we'll know what the wave functions are. We can answer questions like, where is the electron? And why doesn't the hydrogen atom collapse? So the first step is find the energies and the wave functions, and then we can continue to ask further questions. All right, so we're going to do a lot of calculus. It's unavoidable. We're just going to do it. All right, so what we have in the first line is h psi equals e psi. That's the Schrodinger equation. We then substitute in the kinetic and potential energy operator for our Hamiltonian. And when that operates on the wave function psi, we get the energy times psi. And then now we're going to take that Laplacian, del squared, and convert that into spherical coordinates. And that becomes minus h bar squared over 2me times 1 over r squared d by dr, r squared d by dr, plus 1 over r squared sine theta d by d theta, sine theta d by d theta, plus 1 over r squared sine squared theta d squared by d phi squared. So that's just the Schrodinger equation written in spherical coordinates with the potential energy for a hydrogen-like atom. Now this equation is simplified a little bit if we multiply both sides by twice the mass of the electron times the radius squared. Because when we do that, we notice something. When we multiply by 2me r squared, the r squareds cancel out over here and over here, and they leave us with 1r over here. And so we can separate this into two different things that depend on the radius, where the radius is still in the equation, and things that depend on the angles. Right? And notice here, when we have this red term, we have minus h bar squared over sine theta d by d theta. Right? This looks like the Legendrian. No radial dependence in there. And in these two green portions, we have no angular dependence. Okay? This suggests, right, we're writing this up as an operator. So we can rewrite this as an operator that depends on the radius, the distance from the nucleus, operating on our wave function, plus some operators that depend on the angle operating on our wave function. And those equal to 0. What this suggests is that we can make a wave function which separates the angular and the radial components. And we can use the technique known as separation of variables. If you haven't taken differential equations and this technique is unfamiliar with you, just follow along. We're not going to be tested directly on separation of variables, but try and follow along so you can understand where this comes from. Okay. All right, so our separation of variables, we are going to write our wave function, psi of r, theta, and phi, as two separate functions. One, capital R of r, which is going to be a function of the radius, and then y of theta and phi, which is going to be a function of the angles. Now, having put this as y of theta and phi, it should already be suggesting to you that these are going to be the same spherical harmonics that we discussed in class on Friday. And it turns out that will in fact be the case. But let's keep going. Okay. So now what we have is we have my operator that acts on r. We're going to just plug this in. And we're going to plug r of r and y of theta and phi for our wave function psi. Now, I have my thing that operates on r. It doesn't operate on theta and phi, so theta and phi can just come right out. Over here, we have our operator of theta and phi. Doesn't do anything to r of r, and so that can pass on through. and we get something that looks like this. If we then multiply both sides by 1 over the wave function, so multiply by 1 over psi in this separated form, we get the following. We get a function, a set of operators, and we get operators acting on R of R, and we get operators acting on y of theta and phi, where these are angle only, these are radial only. And the only way that that can be true for all values of the radius, all values of both angles, is if, where's my mouse? Is if this portion, this top line, and this bottom line are both equal to a constant number. And we're going to choose that number to be beta. So we're going to solve the following equations. We now get two separate equations for r and y. The first one says that this function, which is all radius dependent, is going to give us our radial function. And that radial function is going to determine how far away the electron is likely to be from the nucleus. This function down here, well, if I just multiply through by y of theta and phi, I'm going to get the Legendrian eigenvalue equation that we just solved in class earlier today. Okay. And so we're going to be able to know that those are spherical harmonic solutions. They're going to determine the overall shape, where in space the wave function points. All right, so we're going to start with the radial portion of the hydrogen atom wave function, because we haven't seen that yet. And it's really the most important portion of the wave function you can think of, because if we go back here and look at it, the energy of our system is up here in this radial portion. In other words, the energy of the hydrogen atom is only going to depend on our values for R. Went backwards there. Okay. So we come back down here. I'm going to use some foresight. And we said it was going to be equal to some number beta. I'm now going to change beta into a slightly different form. I'm going to make beta equal to L times L plus 1. And that makes sense since we've already studied the spherical harmonics. We know that L times L plus 1 is going to come out naturally in our spherical harmonics. Once I make that little change, I'm going to multiply both sides by capital R of R, by our radial function. And now we have three separate terms over here. We have an eigenvalue equation. So this is an operator. It's a function of radius that operates on our radial function, is equal to the energy times our radial function. And we have three different components of this. The first component on the left here, this is the radial kinetic energy. This is the kinetic energy that's due to the electron moving in and out towards and away from the nucleus. That's always going to be a positive number. It's kinetic energy, so that's always going to be positive. And we know that that number, we can expect a couple of things. We can expect that number to be larger when the electron is close by the nucleus, right? Because it'll be effectively confined more to be near the nucleus. When it's far away, we expect the radial kinetic energy to be low. We have the Coulombic attraction, right? That's the attraction that the electron and the nucleus feel for each other. That scales like 1 over R. So at long distances, they're not very attracted. At short distances, they're extremely attractive. And then this term over here, this last term, that looks like something related to the angular momentum. We see that L plus 1 times h bar, divided by something that looks like a moment of inertia. 2 times the mass times the radius squared. That actually comes from centrifugal force. Right? So if we have this electron that's going around the hydrogen nucleus, then as it moves, right, there'll be a centrifugal force that wants to push it out. And the more that's spinning, the higher the value of L is, the more it's going to want to be pushed out. Okay, so let's take a look at this a little bit better here. Right? So we have radial kinetic energy is the energy required to confine the wave. And it gets larger when the wave function is confined to a small range of radii. So the closer the electron gets to the nucleus, the larger the radial kinetic energy is going to get. We have the Coulombic attraction. the attraction of the electron to the nucleus. And we have the centrifugal force term, which is down here on the bottom. And it's going to increase with L. Now, importantly, when L is 0, when there's no orbital angular momentum, this term is 0. And doesn't, right? There's nothing there. When L is 1 or more, right, then we can look at it at very low values of R. This goes like 1 over R squared. This goes like negative 1 over R. And for very small values of R, this repulsive term is going to be larger. And so when L is equal to 0, if we look at this as an effective potential of the kinetic energy of the attraction plus the centrifugal force, when L is not equal to 0, we're going to get this repulsive barrier to the electron getting close to the nucleus because of the centrifugal force. And then at long distance, we're going to get Coulombic attraction. Whereas when L is equal to 0, we're not going to have any centrifugal force. And so the potential energy is just going to go to minus infinity as R goes to 0. So for L greater than 0, there's a large centrifugal barrier that pushes the electrons away. For L equal to 0, there's no angular momentum and no centrifugal barrier. And it's going to turn out that our radial wave function is going to have a finite value at the nucleus. When L is greater than 0, that finite value, that radial wave function is going to go to 0 at the nucleus. There's not going to be any probability of finding it there. And then far from the nucleus, our effective potential looks like minus 1 over R regardless of angular momentum. And we expect R of R to go to look the same as R goes to infinity, no matter whether it has angular momentum or not. Okay. We still need to solve this. This is an eigenvalue equation, and solving for it is incredibly tedious. And we're not going to do that. Instead, we're going to sketch out some of the factors of the solution. So the solutions are given as a polynomial as a function of R. So something like R cubed minus something times R squared plus something times R minus 7. Right? It's going to be a normal polynomial times an exponential decay. Something that looks like e to the minus R over some length. And these solutions are going to be characterized by two quantum numbers. The first quantum number is going to be n, be the primary quantum number, and that's going to determine the energy. The second quantum number is going to be L, and that's going to be determined by the angular momentum. Right? And so we're going to get different radial wave functions if our electron is carrying orbital angular momentum or not. And it's going to get it, from the more orbital angular momentum it is, we're going to get different wave functions for each value of L, remembering that L can only be 0, 1, 2, 3, or any other whole number. All right. So the shape is going to be something that looks like R to the L. This is our centrifugal barrier term, plus a polynomial in R, which is going to be determined by our primary quantum number, times e to the minus some number times R. So an exponential decay. So at long distances, it's always going to look like an exponential decay. And the energy is given by the following. The energy for the hydrogen atom is the reduced mass times the charge of the nucleus to the charge of an electron to the fourth power, divided by 32 pi squared epsilon naught squared h bar squared, times the atomic number squared, divided by the principal quantum number squared. So for any given hydrogen atom, all of this just constitutes one number divided by n squared. Now, a little bit of bookkeeping notation. To be exactly right about this, to be formally accurate, we have the reduced mass of the electron and the proton, which is very close to just to the mass of the electron. And then when we talk about the wave functions, we have a couple of things. We have A naught, which is this value here, 4 pi epsilon naught h bar squared over the mass of the electron times the charge of the electron squared. you work out the units, this ends up being a unit of length. And that unit of length is 0.529 angstroms. And it turns out that that's going to be the most probable spot to find the electron in a 1s orbital. Alpha, over here, this parameter, it scales the mass by the reduced mass. Right? So it scales this length by the ratio of the electron's mass to the reduced mass. And then rho is a dimensionless length. And it's 2 times the atomic number times the radius, how far away the electron is from the nucleus, divided by alpha, which is almost exactly 5.29 angstroms, divided by the principal quantum number. Okay. So this is really something that looks like, and this rho is going to show up in the exponential decay, and it's going to look like e to the minus r over some integer, n, times the Bohr radius. And that's going to be the basic fundamental large radius decay of our wave function. So we're going to have normalization constant, rho to the L, polynomial of rho, and then e to the minus rho over 2. E to the minus r over some number times a naught. Okay, so an exponential decay. Now, a couple of things to note. That exponential decay decays faster when z is large. Right? So when z is large, then the electron is more attracted to the nucleus, and the electron sticks closer by. It doesn't extend as far out into space. When the quantum number increases, right, when the energy increases, that exponential decay gets weaker. And so the electron gets further and further out for larger and larger quantum numbers. And it turns out that the quantum number, I should point this out, the quantum number n can take on values from 1, 2, 3, 4, etc., any of the natural numbers. It can't be 0 and it can't be negative. For any given value of n, L, the angular momentum quantum number, can range from 0 to n minus 1. Okay. And the first several hydrogenic radial wave functions are written explicitly over here on the right. They're also given in your book in table 8A1. Okay. So these are the radial wave functions that are solutions to this particular eigenfunction. This particular set of operators. They're the eigenfunctions of this eigenvalue equation. Okay. Now, that doesn't actually help us understand what's going on too much, so instead what we want to do is we want to visualize them. And so here they are. Here are the first several radial wave functions. They depend on they depend on the principal quantum number, n, which is going to be the shell that we're talking about, right? So you have a 1s, 2s, a 3s. What that means is that n is equal to 1, n is equal to 2, or n is equal to 3. And as we go from left to right, so as we go up, we're increasing n, the principal quantum number, and as we go to the right, we're changing the orbital angular momentum quantum number. Right? So we're going from L equal to 0 at an s orbital, L equal to 1 at a p orbital, and L equal to 2 for a d orbital. Now, let's take a look at this. For the s orbitals, you can see that the radial wave function is some finite number at 0 at the nucleus. Whereas for L equal to 1 and 2, it always goes to 0 at the nucleus. And that's because of that centrifugal barrier that we were talking about. If we go up, we go from n equals 1 to 2 to 3, right, the wave function gets further and further out. Right? And we also get more crossings at 0. Right? Remember, this looks like a polynomial in r times r to the L. And so it crosses 0 multiple times. So we go up the s orbitals, we have n minus 1 nodes. n minus 1 radial nodes. But notice that when we go over from n equals 2 from a 2s orbital to a 2p orbital, we change L from 0 to 1, we get rid of this radial node. And the reason for that is we end up making an angular node over here. Okay. Finally, if we go up if we look at this 2s versus the 2p, the average location, the average weight of this 2p radial wave function is actually closer to the nucleus than the average value of this 2s orbital. This is actually a little bit closer in on average than the 2s's. But the 2s has this little part here that penetrates and gets very close to the nucleus, whereas the 2p does not. This is going to become important later when we talk about multi-electron atoms and the shielding effect. What we've been talking about, that's the radial wave function, but something we might be more interested in would be the radial probability. What is the probability of finding the electron within a shell of thickness dr for any given value of r? Well, remember, right, because the probability of our wave function, or the probability is psi star psi, and the radial probability is going to be r squared, little r squared, times capital R squared. This little r squared comes from the fact that our volume element in spherical coordinates was r squared sine theta dr d theta d phi. And so if we want to look over this, we need to include that factor of r squared in our radial probability distribution. So because the radial probability distribution, because of that r squared, the probability of finding the electron at the nucleus at r equal to 0 is also 0. Okay? But around the nucleus is a very high probability of finding the electron for an s orbital. Okay? Exponential, so each r of r is exponentially decaying at long r. So when r goes to infinity, our probability of finding r in a given shell goes to 0. And at some intermediate distance, the wave function passes through a local maximum, and that's the most probable location to find the electron. So here, this is a radial distribution function of an s orbital, and we find that it has a most probable location. Where'd my mouse go? It should be a 1s orbital, as the most probable location right here at 1 Bohr radius. So if we go plot the rest of the radial distribution functions, you'll notice 1s, everything is up here close to the nucleus. 2s, we have this node. 3s, we get further and further out. We can directly calculate the probability of finding the electron in a given radius by simply taking the integral over the radial distribution function, the radial wave function squared times r squared dr between two values of the radius. All right, so that was the radial portion of our hydrogen atom wave functions. What about the spherical harmonics that we hinted at? Well, remember, the spherical harmonics are going to be the solution to that equation. We already saw that. Our angular momentum squared operator is minus h bar squared times the Legendrian, which is given here. The angular part of the hydrogen Hamiltonian looks like this. They only differ by a factor of h bar. And so when I operate L squared on this, I get L times L plus 1 times h bar squared. That orbital angular momentum quantum number tells us how much orbital angular momentum there is, just like for a particle rotating on a sphere. M, the other quantum number for the spherical harmonics, M is still going to be the magnetic quantum number. And the reason we call it a magnetic field is that a magnetic field can split the degeneracy of the different M orbitals with the same L quantum number. But again, let's remember what these quantum numbers mean. L is telling us the magnitude of the angular momentum. So how much this electron is rotating around the nucleus versus just sitting still in a semi-classical sense. M sub L is telling us how much of that is projected onto the z-axis. And m sub L times h bar is that amount, and that's always less than the actual magnitude of the total angular momentum, which is the square root of L times L plus 1 h bar. And so for given values of L, we can have different projections onto the z-axis, and the larger that m sub L is, the more it resembles L and the less uncertainty we have in x and y. When m sub L is equal to 0, right, then we're rotating in the xy plane, and we have maximum uncertainty in x and y. Right. These wave functions are also an eigenfunction of Lz, right? When we take Lz and operate on the spherical harmonics, we get mh bar times the spherical harmonics. And then finally, the full solution to the hydrogen atom wave function is just multiplying the radial wave function by the angular wave function. Okay. So just a reminder, the radial wave function is capital R, depends on n and L quantum numbers. N is the principal quantum number, it determines the energy. L is the angular momentum quantum number. The angular components are spherical harmonics, and they determine the orbital shape. They are also eigenfunctions of L squared and Lz. They have a total angular momentum of square root of L plus 1 h bar, or square root of h bar squared, which is h bar. And the total angular momentum about the z-axis is m sub L times h bar. All right, so let's take a look at a couple of these. Let's look at the 1s orbital. So here we have the 1s orbital. The spherical harmonic, 1s orbital, principal quantum number is 1. The only value that L can take is therefore 0. And if L is 0, the only value M can take is 0. If we look at y00, that's just 1 over the square root of 2 pi. 1 over 2 square root of pi, sorry. And the radial function we can go look up from our table is just a simple exponential decay. An important thing to note is that s orbitals are always spherically symmetric, since the angular wave function has no nodes. And a 1s orbital has no nodes at all. Shown over here on the right is a cut through of the probability density for the 1s orbital. It's 0 directly at the nucleus, it peaks at about 1 Bohr, and then it decays exponentially away. Let's take a look at the 2s orbital. 2s orbital, I have the same, for a 2s orbital, I have the same angular component. I have the 0, 0 spherical harmonics, so that's just a constant number, 1 over 2 square root pi. But my radial wave function down here now has a slightly more complicated value. I have 2 minus rho times e to the minus rho over 2. Right? And so I'm going to get a node right here when rho is equal to 2. Right? When rho is equal to 2, this is a node, this is equal to 0, and that's this radial node right here. And there's no probability of finding the electron in that particular shell, right, at that particular value of the radius. So still spherically symmetric, but also have one radial node. That's psi 2, 0, 0. Let's look at psi 2, 1, 0. That's a p orbital. Okay. So now we need to go look up the radial wave function and the spherical harmonic. And that spherical harmonic looks like cosine theta. Radial wave function looks like e to the minus r over 2a naught, so it decays more slowly than a 1s orbital, but the same decay rate as the 2s orbital. But when we multiply that cosine theta times that radial function, we get that it has this lobed structure that points along the z-axis. That lobe points along the z-axis. This is why we call this a pz orbital. We call it a pz orbital, psi 2, 1, 0. In fact, whenever m sub L is equal to 0, we get a wave function that points along the z-axis. But what about the other two values that m can take? What about when m is equal to +1 or -1, psi 2, 1, 1, and psi 2, 1, -1? Well, visualizing those is difficult because they're complex. But they have the same energy, right? The energy only depends on the principal quantum number. So I can take a linear combination of them. I can add those two together or subtract those two and get real orbitals. So here is the actual, here's the angular component for for y1 plus 1 and y1 minus 1. We get the following form. We get some constants times sine theta e to the I plus or minus phi. But if we add these two together, we can get a py orbital. And if we subtract them, we get a py orbital, an orbital that points along the y direction. So notice that all three of these p orbitals have one angular node and no radial nodes. But when we say px and py, we're looking at orbitals that are linear combinations of p plus and p minus, or psi 2, 1 plus 1 and psi 2, 1 minus 1. If we go to the d orbitals, we're going to again get complex wave functions that are going to be e to the I 2 phi, e to the I phi, e to the 0, e to the minus I phi, and e to the minus 2 I phi. But if we take linear combinations of those, we can get the d orbitals that point along specific axes that you're familiar with. And so we can get the dxy, the dxz, the dyz, the dx squared minus y squared, and this is the dz squared. And the dz squared is the one where m sub l is equal to 0, and it points completely along the z-axis. Okay. All right, so just a review of the nodes in the hydrogen atom. Oh, that's a mistake. The number of nodes in a hydrogen atom-like wave function is n minus 1. The number of angular nodes is equal to L, and the number of radial nodes is equal to n minus 1 minus L. Right? And that tells us how many nodes we have, and whether those nodes are going to be angular or radial. Combining all of that information together, we can make visual charts of what our different orbitals look like. We can make some really nice, pretty graphs. Here we have, as we go across here, we're going to increase the principal quantum numbers. We're going to be increasing the number of radial nodes as we go across here. And as we go down, we increase the number of angular nodes. Okay. This is a gallery of the different single electron atomic orbitals for the hydrogen atom. And we're going to use these as our building blocks for looking at multi-electron atoms. We're going to look at helium, and we're going to look at lithium. But before we can do that, we have to take into account something that's very interesting, which is the quantum mechanical property known as spin. And that's what we'll talk about when we come back to class on Friday. Thanks for watching. I hope this was helpful, and good luck on the homework. Thanks a lot, everyone.